Hello, this is Professor Jimenez, and today we're going to see how to design a Bargraph temperature indicator. The lab practice number varies depending on the course you're taking. In this project, the PIC Micro will sense the ambient temperature using the classic LM34DC temperature sensor. This sensor delivers a linear output of 10 millivolts per Fahrenheit degree. And there are many levels that we can detect. In this case, we have 5 levels for the circuit. But and notice that the sensor, it is connected on analog input 1 or RA1. RA1 is when it is digital, AN1 when it is analog. So, well, even when we are applying this here, we can change it depending on the code. And according to the previous practice, you're not limited to using only 5 LEDs. You can also design it using 10 LEDs, as this is the case, and you can place the temperature sensor right here. And then this will be the circuit, RC0 to RC7 with a 10 bar graph LED, 10 LED bar graph. And so we don't need the piezo buzzer in this case. And with the analog input, we are measuring, in this case, different temperatures, 72 Fahrenheit degrees. And for that case, the sensor will deliver 10 millivolts per Fahrenheit. So you have to multiply 72 times 10. That's 720 millivolts. For 74 degrees is 740 millivolts, and so on. For 80 degrees is 800 millivolts. So, and we can detect wide the temperature range. So we can decide here if the temperature is less than 72, we can put a LED1 flashing, or if the temperature is greater than 84, we can have the last LED flashing. So we can modify that at any time. And to understand how these voltages are generated and how we convert them to binary code or hexadecimal code, in this table we have here on the left side here, this row represents the bit number, the units. So notice that the bit numbers are here. Bit 7, which is the most significant bit, and bit is 0, which is the least significant bit. And the resolution in millivolts, according to the equation we saw in the previous experiment, it is 5 volts divided by 2 to the n minus 1, so it is 19.60. But I'm rounding off these 19.60 to 20 for practical purposes. For the first 5 bits, we can say 20 times 2 is 40, times 2 is 80, 20 times the binary weight 8 is 160, then double this to 320, 640. But right here, I'm not using 1280 because that will be out of range. So to reduce the error and maximize precision, I'm multiplying 20 times 64. So that'll be, or 19.6 times 64, that will be 1250. And right here, 2500. So 2500 millivolts, which is 2.5 volts, or right here, 1.25 volts. For this case, will be 0.64 volts and so on. So to represent 60 Fahrenheit degrees, which is 600 millivolts, we have to get the sum of these bits equal or approximately equal to 600. So right here we have 320 plus 80 is 400, 560 plus this amount, I'll get 600 millivolts. Okay, to get 700 millivolts, I represent 70 Fahrenheit, so I have 640 plus 60 is 700, you see? Now I have here 720, so I just add to the previous number. You see I was in number 3 here in binary code, then I moved to 4. So I will have 640 plus 80 is 640, where am I? Right here. Yeah, 640 plus 80 plus 20, and that'll make 720 millivolts. And so you can see that the additions that you get here is equal to the number, to the amount in millivolts that you're expecting. Like right here, 800. So it is 640 plus 160 is 780 plus 20, 800 millivolts. So these amounts represent exactly in binary code the temperature. 900 millivolts, which is the last case. I'm skipping many lectures right here, which you can fill in those empty spaces. So the 900 millivolts will be 600 plus this amount, plus 160 plus 80 plus 40, and that'll be 900. So this is how you use those binary codes. And for example, you can represent the 70 degrees in binary code, because if you use these 4 bits, okay, this is number 2, okay, and this is number 3 in hexadecimal code. So this code is 23. So for example, for 74 Fahrenheit degrees, you have here number 2 in hexadecimal code, and right here you have number 6, so that'll be 26, you see. For 72 degrees, that'll be 2, number 2 right here, and number 5 right here, so 25. So, but you can use both methods in binary or in hexadecimal code. So now that we have the table, we will use channel 3 using this instruction, where this is the ADC input, this is the channel, and the voltage will be stored in this variable, the variable volt. So now if you want to make comparisons, you can say if volt is less than 25, in other words, if it is less than 74 Fahrenheit, go to flash LED 1. So the first LED will be flashing. If volt is greater or equal than 26, so if the temperature is equal, greater or equal than 76 Fahrenheit, then turn on the LED, the first LED on RC0, okay? If this condition is true, if it is, and the sensor will be increasing the temperature. So if the first one is true, and the second one is true, probably the other ones will not be true. So only the LEDs with the true condition will turn on the respective LED in a bar graph mode, because we are using the greater than or equal than, okay? And if you just need to detect if it is greater than, for example, 84, which is 2F in hexadecimal, then you will go to this label, flash LED in a second method. And in this way, jump to this method and flash the LED in a way that we will see in a moment. So all these $sign 26, 28, $sign is hexadecimal code, and the hexadecimal code is represented right there, okay? And as I said, if you want to use a binary code, you can represent it using the % symbol. And then after you do the comparisons, the LEDs will turn on for microseconds, but you want to hold them for 50 milliseconds so that your eyes can detect them. And that way, we don't need more readings. You have 50 milliseconds, so and you go to repeat to take a new reading and do this again. That'll take microseconds. So in this case, we can say that you are taking 20 readings per second, but you want to take 10 readings per second, so that'll be 100 milliseconds, and 100 milliseconds fits let me put it here, fits 10 times in a second. So that will be, we can say 10 readings per second. If that is too much and you want to have 5 readings per second, do it this way, 200 milliseconds. Okay, and you can increase this time. So if you just want to take readings every second, you have to put it 1000 milliseconds. So right here. Remember, you cannot use decimal points right here, only integer numbers. So pulse 1000 is 1000 milliseconds is 1 second. So you take 1 second, that means you're taking a reading every second. Okay. Now, if we start with the code. First, we name the practice, today's date, the resolution, the PIC Micro. Those are your nodes. Okay. Then first, we declare a variable bold, which is, by the way, I have to express it this way. So bold is a variable byte, I is a variable byte. And because we will use these two variables to allocate memory space in the code. And first, we do this to make ports to set port A as an input, okay, as an input, and uncell A, which is the other part of configuring port A, is all ones from RA0 to RA5. That way, port A is analog. All port A is an analog input. Okay. Port B is set as an output. Port C set as an output because it'll be driving the LEDs. Okay. And then right here, port C is set as digital because we don't want to take any voltage reading on port C. Then this is this is for pull-up resistor. We don't need them at this moment. And this is the FM bit, which will give us write justify format readings. We saw that in the lesson regarding the A to D converter. We don't need the latches, so we will clear them. We're not using the pull-up resistors. We want to work at 4 megahertz with 6/8 hexadecimal. We define the A to D for 8 bits, and the clock source for the A to D converter is clock source number 3. It's an internal RC oscillator, and the sample and hold 50 microseconds. And so we clear the 3 ports before starting the code. So now we do the comparisons, voltage comparisons. So this is our first label. We call it repeat. So first, clear port C equal to 0. I know I clear it right here, but I need it in this area. So now I'm taking, let me amplify this a little. So I'm taking my first reading with ADC in 3. So right here, what I'm doing is I'm reading channel 3, or you can change it to channel 1, okay, RA1, AN1, or AN0, AN2, AN3, in this case 3, and read AN3 and store the reading in the variable called volt, which I defined previously as a variable byte right there. Okay, so now if volt is less than 22 hexadecimal, then go and flash. So if the temperature is less than 22 hexadecimal, we can go to the table, we can go back, and we can see 72 right here. 72, it's the code is 4 bits right here, so it's 2, and right here I have number 5 in my area, so it's 25. 25 corresponds to 72 Fahrenheit degrees, 25. So if the temperature is less than 70 Fahrenheit, flash, go to this label and start flashing the LED. Okay, we will see that label in a moment. If that is not true, if the temperature is greater than this or higher than this, so now we take another reading, because we make another comparison. We take another comparison. If bold is greater than 72 degrees, okay, then turn on port Z.0 equal to 1. Okay, you want this instruction to perform comparisons greater than or equal than. You can add the equal right here. So if the temperature is equal or greater than 72, turn on RC0. If it's greater than or equal than 74, turn on RC1, the second LED. If it is equal than 27, which corresponds to 76 Fahrenheit, turn on RC2. So depending on which one is true, which condition is true, they will be the true condition will be turning on the respective LEDs in a bar graph mode. Okay, if the first ones don't comply, the other ones will never comply, because the temperature is increasing from lower to high. Okay, so you can add these equals to the code right here and right here. So once you have these LEDs turn on depending on the temperature, if the temperature in this case is equal or higher than 88 degrees, for example, you say, I just want to know if it is higher than 88, and higher than 88 will be 89 and 90 and so on. So then go to this label. Okay, so now once this is performed, the next instruction will be wait 50 milliseconds or 100 milliseconds if we want to have 10 readings per second, and then go to repeat. Okay, so it starts taking new readings because the repeat is right there, the label. If the conditions for example, if the temperature is less than 22 hexadecimal, which is 70 Fahrenheit, if it is less than 75, you have to go to this label. The code will jump right here. So it'll do 2 times for I equal 1 to 2 times clear port C for this for 50 milliseconds, and turn on RC0 for 50 milliseconds. Increment I, and then I goes back here, because for every 4 you have a next. So you will do this 10 times, 2 times right here. So 50 milliseconds and 50 milliseconds on, plus all 50 milliseconds off. So it will flash 2 times at this rate, which corresponds to 10 Hertz. That's the rate. And once it is finished twice doing this, it will go back to repeat. So it'll take a new reading. If the condition still prevails, it'll keep flashing the LED. If the condition is not true, it'll turn on LEDs in a bar graph mode. That is, the temperature, as we saw here, is higher than 88 degrees. So if it is 89, 90 degrees, it'll jump to this label, flash LED2. So, and again, it'll do this twice, okay? But now it'll not turn on port RC0 like before. No, now it'll turn on port C5, the LED on RC5, okay? Because I changed the port right there, okay? This at the same rate, and you can change the rate, of course, right here. You want to flash it higher or lower, and then you go to repeat, and this is the end of the code. So it is a simple code, but it is very interesting how you can do the comparisons and how you can change with this table. You can change the temperature, because I can ask you to detect other temperatures, different temperatures, and notice that here we're not using these 2 bits, so we are not detecting temperatures higher than 125 degrees or 250 degrees, unless we will have an industrial application. But just to finish this lesson, right here, I have a case. For example, if you want to turn on just one LED at a time for a temperature range, for example, if volt, what is volt? Is the voltage delivered by the temperature sensor. So if the temperature is higher than 23 hexadecimal, which is 70 Fahrenheit degrees, and the temperature is less than 26, which is 74, okay? If the temperature is higher than 70 and less than 74, okay, then port 3.0 will be equal to 1. So in this case, only one LED will be turned on if that LED, and that LED will indicate that the temperature is within this range, okay? Because many times you just need to know if it is in that range. Now you want to change, you want to have more comparisons like this one. We can do this. We can change those ranges and develop a new code. For example, you can change the code right here. Now for the second LED, this will be the second LED, the third LED, fourth LED, the fifth LED. You see, you just change this. And how will you change the code, the range? By changing the code right here. So you can change this number to another number that you are interested, okay, right here. Same thing right here. You can change that range, okay, and that way you can apply it to a very specific application that you have in mind or that you need for a commercial or industrial application. And industrial applications, that depends on what type of sensor you will be using. So you can see here that you can change that code. And the code, as I said, it can be in hexadecimal because it is easier to get it from the table. But and then every time you change this, you have to change this text, the ranges, okay? And right here, change the text. So you can do something like this. And this is the syntax. This is how you write the code to compare if a temperature is within the range that you are specifying here. So that will be a homework that I will be assigning in our group. But now you know how to start solving that homework. And of course, every time you write this code, you can, for example, you can change this $sign to %, which is binary code, and this can be binary code too. So you use the %. So for example, let's go to the table. If you want to detect if the temperature is, let's say, 884, so 80 and 84, or within 80 and 82 degrees, you see that range? What code do we have here? 22. We have 9. This is number 9 in binary, and this is a number. Well, in Xcode is it is. I said between 80 and 82. Okay, so we have in X 20, 25, and right here 2A. So I can see it is 25, 20, no, 29, 29, and 2A. Okay, so 29 and 2A. So we go here, and this is how you will do it. I know I said 20, so it'll be this 28. There, that's in binary. There it goes. And right here, 20, 29. That's 2. And number 9 is 1001. Okay. This is another way, another method to write the code in there it goes. To write the code in binary comparisons right here, not hexadecimal numbers, but binary. And the compiler accepts this, of course. And we said that if the temperature will be, that we will be detecting 80 and 82. Okay, so we just have to change the text. 80 and 82. 80 and 82. So that LED, this second LED, will be turned on only when the temperature, only when the temperature is greater than, if it is greater than 80 and less than 82 Fahrenheit. So, and you can change also here, and you can play with the codes in binary or hexadecimal. So that's all for today, and pay attention to the lesson because on the group, because I will give you an assignment to change this table. Okay, and you can fill in those empty spaces according to the homework. Okay, that's all for today. Thank you very much.